Hello viewers, I am Kausalya. Today we are going to discuss about correlation between time domain and frequency domain specifications. So just for our consideration, here we are taking a second order system. So what is the standard format of a second order system? It is given by omega n square divided by s square plus 2 zeta omega ns plus omega n square. So here the zeta is nothing but damping factor and omega n is nothing but undamped natural frequency. Right. Now we are going to discuss about frequency domain. Right. So frequency. So here we have to substitute S as j omega. So the next step is we are substituting S as j omega. So when you substitute in the standard expression here, you see our expression gets modified like this, right? In the place of yes, just substitute j omega. So j square is nothing but that is minus 1, right? So here you see j omega whole square becomes j square is minus 1, so minus omega square plus the remaining terms remains as such, right? So the next thing is from the denominator term, here omega n square is taken commonly outside. So when you take omega n square outside, what happens? Here this term becomes minus omega square divided by omega n square plus for this expression, this entire expression will be divided by this omega n square and finally omega n square by omega n square, right? So here these two terms cancel each other and finally here there is an omega n and there is an omega n square. So these two cancel and finally the remaining terms will be here in this place we will be having 1, right? So I am combining real terms together. So here 1 is the real term and this expression minus omega square by omega n square is the real term. So in the next step I am combining those two terms. You see 1 here becomes 1, right? And these two are same, so they cancel. So 1 divided by 1 minus omega by omega n whole square, because here both these terms have squares, plus here j 2 zeta omega by omega n. So here we are having like this, right? Since we are having omega by omega 1 n, here we are representing that term as u, right? And this is known as normalized frequency. So when you substitute omega by omega n as u, our expression gets modified as 1 minus u square plus j into 2 zeta u, right? So for this expression, we are going to write the expression for magnitude. So how to write the expression for magnitude? That is, we have to take square root and we have to square the elements inside. So here we are having 1 minus u square, right? So square root of 1 minus u square whole square plus and here 2 zeta u the whole square, right? So when you simplify this expression, this term we are not expanding, okay? We are keeping it as such, so write it. And here 2 zeta u whole square is 2 square is 4 and zeta square is again zeta square and u to the power 2 is u square, right? So the next step is we are going to calculate the resonant frequency. So how to calculate the resonant frequency? We have to differentiate this expression with respect to u, because here we are having u, right? U also stands for frequency. What is u here? U is nothing but here omega by omega n, right? So here I had written as we are going to differentiate them with respect to omega, which is nothing but frequency, but mathematically let it be u here, then only it will be easy for you, right? Both are same. And we are going to equate it to 0. Why we have to differentiate and equating? Because we have to find the resonant frequency, right? So here I have to differentiate and equate it to 0, right? So this is my expression for m, right? I am having the terms in the denominator part. So I am going to shift these terms to the numerator. So here you see This is my term and I am having a square root, right? So this square root can be written as whole to the power of 1 by 2. And this denominator term, when it is moved to the numerator, we have to write it as minus 1 by 2, right? These are all the basic max terms, right? Max concepts. And next step, I am going to differentiate it. So everybody knows the basic differentiation formula, right? So how to differentiate? When you differentiate an element like this, a to the power n, we have to write it as n into a to the power n minus 1, right? This is a base. Again, this is a formula from differentiation. So here I am considering this entire expression as a, right? So here this is a and this a to the power minus 1 by 2, right? So how to write it? Again here n is this minus 1 by 2. So n into, this is my a, right? This entire term I am taking it as a. So write your a as such to the power n minus 1. So here the n is minus 1 by 2. So minus 1 by 2 minus 1, right? So again we are having some terms to differentiate. So this is the basic step. So after writing it, again look into the terms. Here you see, here you are having a term with u, right? Now we are differentiating with respect to u. Keep it in mind always. So again I have to differentiate this term. So how to differentiate? Again, for differentiating this term, consider this term as a, right? A and the power is 2. So how to differentiate? N, here n is 2, right? So you see 2 into, again here a to the power n minus 1. So 2 minus 1 is 1 here, right? So again I am having a u term after differentiation. Again I am having some u terms with power. So I have to differentiate this term again. So how to differentiate? Again the same concept, a to the power n. In the place of a I am having u. And in the place of n I am having 2. And I am having a minus sign also. So keep this minus sign as such here. And this 2, that is n into a to the power n minus 1. So 2 into u to the power 2 minus 1. So I will be getting minus, that is 2u here, and this minus sign comes here as such, right? Again here I am having plus, so write the plus here. So here I am having 4 zeta square. So write this 4 zeta square as such, and when you differentiate u square, you will be having 2u, right? Hope I had explained up to my level. Am I making the concept clear here? Just basic differentiation, but you have to do it carefully. That's it, right? Then the next thing is, so we are solving this expression. You see here I am having the power minus 1 by 2 minus 1. So minus 1 by 2 minus 1 will give you minus 3 by 2. Okay, so write it. And again here you see, here I am having 2 into minus 2u will give you minus 4u, right? And here also I am having 4u. Here I am having 4 and u. So I am taking it commonly outside. Okay, that is done in the next step. So in this step just I have multiplied, that's it. 2 into minus 2u minus 4u, and here this 1 minus u square, here 1 minus u square, and again 4 into 2 is 8, right? So 8 zeta square u, right? And again the next step I had differentiated, right? Now I am going to equate this expression to 0. So here I had written as 0 here. Again we have simplified, that's it. Here there is the term with power minus 3 by 2, right? When I write this term in the denominator term, then this minus 3 by 2 will become plus 3 by 2. That's the thing happened here. And again here in both these cases, when you look both these terms, here 4u is common. So when you take 4u outside, what are all the remaining terms I will be having? When 4u is moved outside, what are all the remaining terms? Minus 1 minus u square, this term I had written here, plus again when you take 4u here, the remaining terms will be 2 zeta square, right? So here I had written the same steps. Now what is the thing? I am equating this to 0, right? So here we are having two terms, right? This is one term and this is two term. In these two terms, if any one term becomes 0, then the answer is 0. Do you accept? Because these two terms are in multiplication. There is a multiplication sign in between, right? So just for our analysis, here I am making this term as 0. So when you equate this term as 0, you see what happens. That is 4u into minus 1 minus u square plus 2 zeta square is 0, right? When you move this 4u to the left hand side, what happens? 0 divided by 4u is again 0. So here 0 equal to minus 1 minus u square plus 2 zeta square, right? So I am moving this 1 minus u square term to the left hand side. So this minus term becomes plus here, right? This minus term becomes plus here, which is equal to again 2 zeta square. I need u square again, right? So this u square is with minus sign here. So I am moving this minus u square to the right hand side. So that becomes plus u square. Wait, I'll show you. You see 1 is here, right? This minus u square I am moving to the right hand side. So what happens? That become plus u square plus here this 2 zeta square as such. But what I want actually, I want u square. So I am keeping this u square in the right hand side as such, and I am moving this 2 zeta square to the left hand side. So here I will be having an expression as 1 minus 2 zeta square equal to u square, right? So I want only u. So when you want u, just you have to move this 2, that is you have to take square root on both sides. So u is equal to square root of 1 minus 2 zeta square, right? So what is u? We had seen before, u is nothing but ratio of omega by omega n. Since we are discussing about resonant frequency, here I had written as omega r, right? So omega r by omega n is nothing but again this expression. So omega r is nothing but omega n into square root of 1 minus 2 zeta square, right? Then we are going to calculate resonant peak, right? So resonant peak, it is the maximum value which is obtained by a system, right? So here this resonant peak is obtained by substituting the value of here, that is by substituting the value of u, we are going to find the resonant peak. So what is the basic expression here? This is our basic expression for a magnitude. Since I am calculating resonant peak, here I am writing MR, okay? The resonant peak magnitude, this R denotes that thing, resonant peak magnitude. So here in this case, I am going to substitute the values of u here, right? So what is the value of u? You see the value of u is square root of 1 minus 2 zeta square. You see when you look at the expression carefully, I am having u square, right? So you can directly substitute the value of u square because it will be easy. So here I am having u square, right? Now we are going to substitute these values here. So when you substitute, you see you can omit this term. Okay, I had substituted u and again I had squared it, no need to do that. So this is my expression and I know the value of u square directly, right? So just substitute the values here. So I am having this expression. Next step, I am going to move this minus sign inside. So when you move this minus sign inside, what happens? 1 minus 1 plus 2 zeta square, the whole square, plus here these terms, they won't change, right? Because there is nothing to do with this. So write this as such. So this 1 minus 1 cancel each other. And here I am having, that is here I am having 2 zeta square, the whole square, right? So when you square it, what happens? 2 square is 4 and zeta square to the square is zeta power 4 plus this term I am having as such. And the next step, when you observe carefully, you see I am having 4 zeta square. Here I am having 4 zeta square and here also I am having 4 zeta square, right? Because you can write this as 4 zeta square into zeta square. So I am taking this 4 zeta square commonly outside. So when you take this outside, the remaining terms will be here I will be having a zeta square plus this term 1 minus 2 zeta square. So again when you solve this, what happens? This zeta square minus 2 zeta square gives you an answer of minus zeta square here. So finally, this is the expression for resonant peak. It is given by 1 by 2 zeta. When you solve this, this becomes this plus 1 as such, and zeta square minus 2 zeta square gives you minus zeta square. So this is our expression for resonant peak. So finally we had find out the expression for resonant peak as well as for resonant frequency. Right. Now we are going to compare time domain specifications and frequency domain specifications, because we are going to find what is the relationship that exists between these two. So in time domain specifications, right, this is the formula. Those who have any doubt, just kindly go back and check this, right? So omega d is given by omega n into root of 1 minus zeta square, and mp is given by, that is peak overshoot, is given by e power minus zeta pi divided by root of 1 minus zeta square. Right, I have discussed about these topics long before and I had made separate videos for this. Even if you have any doubt, go back and check it, right? So now we are having expressions for MP and expression for MR. So just look carefully. Here MP, in this expression, we are, this MP depends upon zeta, right? Because you see pi is a constant here. Here it depends upon, I am having a zeta here and I am having a zeta here. Similarly, when you look at the expression for MR, again this MR value depends upon this zeta. Okay, that is damping ratio. Right. So this is a unique feature, right? Because this is our frequency domain specification and this is our time domain specification. But in both the cases, the peak value depends upon the damping ratio. So here, that is our first statement. Both MP and MR are functions of damping ratio. Right. Then the next thing is, in time domain, when zeta increases, MP also increases. Sorry, MP decreases. Just you can do this. You can substitute random values of zeta and check what is the respective values of MP. Right. So whenever zeta increases, the value of MP get decreases. Right. So here, whenever the zeta value is 1, the MP becomes 0. Even you can substitute the value of zeta as 1 here and check what is the value of MP. Right, these are all the simple calculations. So when zeta is 1, MP is 0. So what is mean that when the peak value is 0, the system will not produce any overshoot. That is, the system won't reach its maximum value again whenever the damping ratio is made 1. Right. Then in frequency domain specifications, we are going to analyze when the value of this MR will be 0, because we had find out a condition when the value of MP is 0. Similarly, we are going to find when the value of this MR will be 0. So what is the expression for MR? Just now we had find out, right? 2 zeta into root of 1 minus zeta square. So I have to find when will be the value of this MR 0. So here I am substituting this. 0 equal to, I am having this expression. So from this expression, I am having u equal to square root of 1 minus 2 zeta square, right? Sorry, not from this expression. We are considering this expression, u equal to root of 1 minus 2 zeta square. So here, whenever the value of u equal to 0, that is using this condition, we are going to frame what is the value of zeta, right? So whenever the value is u is 0, that is u equal to 0 means I am having an expression like this, right? So from this expression, by solving, we are getting 2 zeta square equal to 1, and zeta, finally the value of zeta is 0.707. That is, whenever you substitute this value, then we will be having our resonant frequency, that is resonant magnitude, peak value of resonant magnitude as 0, right? You can check. In the previous expression, just substitute this 0.707. When you substitute this value, your MR value will be equal to 0, right? So, during this condition, again, the system will not exhibit resonant peak. Whenever it reaches this value of zeta, again the system won't reach its peak value once again, right? So here, this is the typical diagram which explains that case, right? So this is our resonant peak value. Whenever the value of zeta is less than 0.707, it reaches its peak value, right? But whenever the value of zeta is greater than 0.707, you see our slope, that is the curve is like this. There is no peak values, it simply slides down, right? So is it clear? That is, whenever the value is exactly equal to 0.707, damping ratio, what is meant by damping ratio? It always limits the maximum overshoot or peak overshoot, right? So here, whenever the zeta is less than this value, then there is a peak overshoot here. But whenever it reaches 0.707, then there will be no peak values. You see, our curve is just like this. Whenever the value of zeta is greater than 0.707, right? Then the next thing, we are assuming a smaller value of zeta here. That is, whenever the zeta is less than 0.4. Whenever the value is less, what happens? The damping ratio always reduces the peak overshoot. You should always keep this in mind, right? So whenever the value of damping ratio is very small, what happens? Automatically MP and MR, right? Both these values, that is resonant peak values and the in time domain specification, the peak overshoot. So both these values will be very large, and what happened to the system? The system may get damaged, right? So zeta is always designed between 0.4 and 0.707, right? Am I making the concept clear? Because damping ratio is the factor that decides what is the maximum overshoot value. Right. So whenever the damping ratio is very small, what happens? The peak overshoot, that is the maximum value attained by the system, will be very high. In return, it may even damage your system. Right. So that is the main reason why we are giving much more importance to the damping ratio. So here the reasonable value for damping ratio is 0.4 to 0.707. Right. So next, what happens when the value of zeta is 0? Right, these are just for analysis, we are considering different values of zeta, right? So whenever the value of zeta is made 0, for lesser values of zeta, the value of this peak values is very high. What happened when it is made 0? Again the same case, both the system, just for your clarification, I had written a statement, right? This is a formula, and when you substitute zeta equal to 0, the maximum value is here 1. Right. So the peak overshoot, that is what it means, 100% overshoot. It reaches the maximum value here. But in the case of this resonant peak frequency, when the value of zeta is made 0, that is 1 divided by 0, it is nothing but infinity. So here finally you see the statement, both are undesirable. Okay. It is not practically possible. We will never do this. Just for analysis we are considering. Right. That's it. So whenever the value of zeta is made 0, both the peak overshoot and the resonant peak values are undesirable. They are very, very high. Again, when zeta is between 0.4 to 0.707, what happens? Here the resonant frequency, there is both these frequency values are comparable to each other, right? Here, again, when the value of zeta is made 0, you see, this resonant frequency is equal to, whenever zeta is made 0, it is equal to omega n. And here also again omega d is almost equal to omega n. That is, it should not be happen. Okay, that's the thing. You see here I had given the explanation. When zeta is small, what happens? Omega d is large, and hence the rise time is very small because it reaches the peak overshoot quickly. And similarly, when zeta is small, again omega r is large, and hence the system is more fast in response. Okay, these are all the things just now I had explained. Right. Now again we are going to look at the graph. You see here mr and mp as a function of zeta. Again the same case. Here even you can substitute the values, okay? Just take a calculator, you are having the formula, you can substitute and see. So here you see for this MP peak overshoot, right? So the maximum value should be 1 here. So from 1 it gradually slides down when the value of zeta increases, right? Here, in the case of resonant peak value, you see it exceeds 1. It is much more higher value, almost it is 3. But when the value of zeta is increasing, the damping ratio is increasing, the value of this thing gets gradually reduced. Right. So simply they are representing these peak values as a function of zeta. And the next thing is the ratio of omega r by omega d as a function of zeta is also done here. So the first thing, omega r by omega d, just substitute the formulas. Here I am having omega n, so both these terms cancel each other, and finally omega r by omega d is given by this expression, right? So you see I had taken random values. That is, I had started from 0.1 to 0.7 and I had find out the values of this omega r by, sorry, I had interchanged. Here it is omega r by omega d ratio and here it is zeta. That is damping ratio I had taken like this. So you see, whenever the damping ratio, this is the damping ratio, right? Whenever its value is increased, you just look at the value of omega r by omega d, it is gradually decreasing, right? So here it is 0.98, it is almost nearer to 1 now. So here I have started from 1 here. So x-axis omega r by omega d and in y-axis omega r by omega d and in x-axis zeta, you see it is gradually decreasing, and when it reaches 0.7 you see the value is 0.03 which is almost 0. So here it reaches the 0 value because here it is 0, right? So finally what is the thing we are going to conclude is there is a strong relationship between time domain specifications and frequency domain specifications. Both these terms are correlated by damping ratio. So here we are calculating the values of resonant peak values and resonant frequency values for different values of damping ratio, and finally we are concluding whenever the value of damping ratio increases, automatically the peak value, that is peak overshoot and resonant peak value, get decreases. In turn, even we can say they are inversely proportional to each other, right? Hope you people understand the video well. If you have any doubt, let me know in the comment section. Thank you.